So attributes are semantic visual properties shared by objects. For example, tigers and dogs have tails, giraffes and pandas have spots. Attributes are helpful for recognition because learning one attribute model can affect multiple object category models. And one interesting application is zero-shot learning, where we learn to recognize completely unseen objects using two things: an attribute-based description of those objects, as well as models for these attributes trained on other classes. So tasks that use human-given attribute descriptions assume that we have reliable attribute models that truly capture the meaning of the attribute regardless of what data or what domain they're trained on. But unfortunately, attributes can look quite different across domains. So here we have the attribute having patches for hoofed animals and carnivores, and you see that the patches on giraffes, for example, are quite different than the patches on Dalmatians. So we and other researchers find that an attribute model trained on one domain doesn't actually work well on another. So this knowledge is not well transferable. So the way we propose to deal with this is with domain adaptation. So we'll be given a large number of labeled instances from a source domain. That's not the domain on which we want to make predictions. And we'll also have a very limited number of instances on a target domain, the one on which we do want to make predictions. Then we'll learn a classifier on the target domain by adapting a model trained on the source domain. We find that it's crucial what type of features we use, so I'll talk about that in a sec. And note that our method is simpler, makes fewer assumptions, and performs better than related work. So the particular domain adaptation method we use is called adaptive SVM. It's very simple. So here we have two classes that we're trying to distinguish between, circles and triangles. So we learn a model on the source data. Then when we bring in data from the target domain, that source model misclassifies it, usually. A model that's just trained on sparse target data will usually overfit. And an adapted model still trains on the target data, but regularizes essentially with the source model. This adaptive SVM method has this major drawback that the source model can be two domain specific. So it might emphasize features that are only effective for that same domain, in which case the regularization can actually be counterproductive. We might have negative transfer occur. So the way we want to deal with this, the way we find to be effective, is that we will learn in a feature subspace where the data distributions of the domains are similar. So this will help ensure that knowledge and models are transferable. So we'll perform a feature selection step first and then adapt. So we have data from high-dimensional data from source and target domains. So we perform a feature selection step and pick the 500 features that are similar between the two domains, then train a source and adapt the model to get an adapted model. So how do we pick features? So for each feature dimension, we'll compute Fisher's criterion, where basically we want small separation between the source and target domains, separately for the positive and negative instances. That's what the two equations say. So we'll rank features based on these scores and pick the top 500. So we'll pick the features that are most similar between the domains. We do experiments on this animals with attributes dataset, where we have hoofed animals as our source domain and carnivores as our target domain. So we take 13 attributes, and our features are from the FC7 layer of CAFINet. We have 1,000 images from the source domain for training and only 20 to 100 from the target domain. And again, we train on the target domain. So this is an average result over all of our attributes. So we see that when training data from the target domain is sparse, so for example, only 20 instances, then our method, this is the upwards triangle, which adapts based on similarity, is more effective than all the other methods, including ones that train from scratch on the target domain. And we also have a comparison against the only method in the literature that assumes separate disjoint source and target objects, and we perform better than that method. So in conclusion, we find that we can transfer attribute knowledge, but only if we learn in a feature subspace where the feature distributions are similar across domains. And come by our poster for more info and results.